Let's briefly look at vector space and subspaces. We have already looked at it in the previous session. Let's expand on that a little bit. A vector space is a non-empty set V of objects called vectors on which two operations are defined, that is addition and multiplication with a scalar, that is real numbers, subject to the following. So let's look at certain aspects of this. U, V and W are vectors in V, and A and B are scalars. Now these are the things that has to be satisfied. U plus V is in V. So when we take these two vectors, we add them, that resultant vector should be in V. U plus V is equal to V plus U. U plus V plus W is equal to U plus V plus W. There is a zero vector such that U plus 0 is equal to U. For each U in V, there is a minus U in V, satisfying U plus minus U is equal to 0. Okay, A times U is in V, vector multiplied with a scalar. Okay, then A times U plus V is equal to AU plus AV. A plus B times U is equal to AU plus BU. Ninth one, AB times U is equal to A times BU. And the last one is A1 times U is equal to U. Okay, so these are the things that has to be satisfied for a vector space formed by a set of vectors. Okay, now apart from this, vector spaces may be formed from subsets of other vector spaces. These are called subspaces, and the condition that has to be satisfied for a subspace is that the zero vector of the vector space is in the subspace. Second is, for each U and V in the subspace, U plus V is in the subspace. And finally, for each U, vector U in the subspace, A times U is in the subspace. Now, as we have seen previously, rank plays an important role in all this. So let's look at some theorems related to rank of a matrix. So one of the theorem is invariance of row rank, or in other words, row equivalent matrices have the same row rank. Okay, let's prove this. Let's say we have a matrix Aij of m by n order. Now let B, another matrix, be equivalent to row equivalent to A. Okay, which implies that B is obtainable from A because B is equivalent to A. Now, how would we obtain it? By using a series of elementary row operations. So Ek times Ek minus 1 and so on up to E2 times E1. So these are all elementary row operations times A. Remember, if it is row operations, left hand side; if it is column operations, on the right hand side. Okay, so we can write this as P is equal to PA, where P is equal to ek times ek minus 1 and so on up to e2 e1, which is going to be a non-singular m by m matrix. Okay, so therefore B can be written as P11, P12 and so on up to P1M, P21, P22 and so on up to P2M, and like this up to PM1, PM2 and so on up to PM, and A would be the row 1, row 2 and so on up to row M. This can be written as P11R1 plus P12R2 and so on up to P1MRM. Then we have P21R1 plus P22R2 and so on P2MRM, and this would go on till PMR1 M1 R1 plus PM2 R2 and so on up to PMM RM. Now, if you look at this, you will notice that the rows of B are linear combinations of the rows R1, R2 and so on up to Rm of A. Therefore, every member of row space of B is a member of the row space of A. Now, similarly, if we do something like this, P inverse of B implies that every member of row space of A is also a member of row space of B. So here we did what did we do? We arrived at a row equivalent. Yes, here we have taken that P to the other side by using inverse. So important point here is pre-multiplication by a non-singular matrix does not alter the row rank of a matrix. On what basis? On this basis, and similarly this. Now let's look at the next theorem. Column equivalent matrices have the same column rank, or we can also say that post multiplication by a non-singular matrix does not alter the column rank of a matrix. And the proof of this is pretty similar to what we did here. Row equivalent matrices have the same row rank. There we are talking of column equivalent matrices have the same column rank. So follow the same procedure to prove this theorem as well. Okay. The next theorem, row equivalent matrices have the same column rank. So row equivalent, same column rank. Okay, so let's prove this. A is equal to, let's say, Aij of order m by n. We are talking of row equivalent. So row equivalent of A, which implies that there exists P such that P is equal to PA, since we are talking of row equivalent. Okay, so for every column vector x such that Ax is equal to 0, we have Bx is equal to PAx, which is equal to P times Ax, which is equal to P0, which is equal to 0. Now, since B is equal to PA, A is equal to P inverse of B. So therefore, for every vector x such that Bx is equal to 0, we have Ax is equal to P inverse of B. x, which is equal to P inverse of Bx, which is equal to P inverse of 0, which is equal to 0. Now, since A and B have the same right nullities, they have same column ranks. Similarly, we can have column equivalent matrices have the same row rank. Okay, let's look at another theorem. If R is the row rank of an m by n matrix A, then there exists a non-singular matrix P such that PA is equal to K0, where K is an R by N matrix with R linearly independent rows of A. Now, if row rank R is 0, nothing to prove, because then PA will be equal to 0. So, let rank R be greater than 0. Now, A has R linearly independent rows. So, what happens then? By elementary operations, we can bring these linearly independent rows in the first R places. Yes, and importantly, the last, so the remaining rows will be what? M minus R rows are now linearly dependent or combinations of the first R rows, which means they can be made 0 without changing the first R rows. So, which means A is row equivalent to a matrix B such that B is equal to K0, where K is the first R rows and the remaining will be zeros. K. Now, every E row operation is equivalent to pre-multiplication. So, therefore, there must be a matrix, a non-singular matrix P, let's say, so that PA is equal to K0, where P is a whole set of elementary operations carried out in sequence. Now, instead of doing row operations, we could also do column operations. So, in which case, what will we have? Since we are talking of column operations, we will have AR, post multiplication, will be equal to LO, where the first R rows, columns, are columns and zeros, R rows and the remaining zeros. Okay, so that is space, subspace, and important theorems which are very useful in understanding spaces and subspaces. That's it for now. Bye.